Hey guys, Andy here. So these two power supply boards from Texas Instruments, they may look exactly the same, but in fact in terms of conducted emissions performance, they're actually very different. This one is Rev A, and if you were to put a layout like this into your design and you needed to pass conducted emissions limits for Europe, you'd probably just have cost your company a few $1,000s in redesign and retesting costs. You probably also just cost yourself a few evenings and weekends to fix it. However, this one, Rev B, you'd probably sail through conducted emissions testing first time, and you'd have those evenings and weekends free to spend with the family, and that's what's important. So in this video, we're going to look at the differences between these two boards so that hopefully you can design your switch mode supply right the first time so you can spend the weekends with your family. And if you're troubleshooting a conducted emissions failure right now, this video should give you a few ideas for ways to improve the EMI performance. And just before we start, I want to mention that the reason I'm able to spend time making these free articles and videos is because of all the engineers and technicians and organizations that enroll into my online courses. They offer a step-by-step process to understanding EMC and EMI at the PCB level, and they go into much more detail than I have time to do in these videos. So if you want to dig deeper into the subject, please check out the links below, which will take you to the full course outlines. And please make sure to like and subscribe and share these videos so that they can help as many engineers as possible. Alright, with that said, let's take a closer look at the hardware we're going to use for this case study. This is the TI PMLK Power Management Lab Kit developed by Professor Nicola Femier and his team at the University of Salerno in Italy. It's mainly for teaching the basics of switch mode power supply theory and operation, but since my focus at EMC FastPass is obviously EMC and EMI, that's what we're going to be using it for in this video. And this circuit we're going to use is based on the LM3475 step-down buck controller from TI, which allows 5 to 10 volts on the input and converts down to 2.5 volts on the output at 1 amp. And what I'll be covering in this video are the schematic and layout changes that relate specifically to the conducted emissions performance. So let's go ahead and start with the schematics. Now this is based on a buck topology, which is one of the simplest and most widely used topologies for switch mode supply. The main components in this circuit are the controller, of course, the switching FET Q1, the inductor L1, and the bulk capacitance on the output and the catch diode D1. And this particular controller uses fixed switching frequency, which is set by the values of these external components. And I'll just give a very brief overview of the circuit operation so that we have a context for what we're talking about in this case study. So the controller uses a comparator-based voltage control loop. The voltage on this feedback pin here is compared to a reference voltage internally with a little bit of hysteresis. And when the input to the comparator falls below the reference voltage, the output of the comparator goes low. And when this happens, the driver output pulls the gate of the PFET low, which turns it on basically. And with the PFET on, the input supply now charges the bulk capacitor on the output and supplies current to the load through the PFET and through the inductor. The current through the inductor, it begins to ramp up, and it does that linearly, and the output voltage begins to increase. And as the voltage on the feedback pin reaches the upper threshold voltage, the output on the comparator, it flips to go high, and the P-gate signal turns the PFET off. And now that the PFET is off, the catch diode turns on, and the current through the inductor begins to ramp down, and again it's linear. And as the output voltage falls below the reference voltage, the cycle repeats again. And that's how this circuit works functionally. But in terms of EMI generation, the most important aspect is where are the highest rates of change of voltage and current. And we'll look at that shortly, but first let's compare the Rev A and Rev B designs. Okay, so on first look, there doesn't appear to be a huge difference between these two designs, and actually the only two schematic changes are this resistor and capacitor in parallel with the Schottky diode. And the function of these guys is to act as a snubber network, and these can help to damp ringing on this particular node, and of course ringing anywhere in your circuit is really bad for EMI. And the other change is this 0.01 ohm sense resistor, and this is for making current measurements on this development board. You can actually clip a little current probe on here to passively measure current at this point. So as you can see, this is moved to the other side of the inductor L1. And on Rev A board, this is on the switch side of L1, and on Rev B, it's on the other side. And having this sense resistor on the controller side of the inductor is probably not the safest idea, because this node is whacking up and down from the input voltage to ground with a square waveform. And by adding this loop, what we're doing is increasing the loop inductance, and more than likely we're going to exacerbate any ringing on this node. But also, with a loop area of approximately 1 centimeter squared, the loop itself forms a pretty decent loop antenna structure for efficiently converting conducted noise into a magnetic field. But by moving this sense resistor to the other side of the inductor, the rate of change of voltage and current is now much slower, which limits the ability of the resistor to radiate. So that's a good move. Now, these are the only two schematic differences I can see on the board. But if we move to the layout differences, there's definitely a few here. The biggest one is that they've moved from a 2-layer board to a 4-layer board. And this gives them some advantages in terms of EMI control. One immediately noticeable impact of this is that the gate drive signal from the controller to the PFET can be buried on an internal layer. And we need to take care of this signal in particular on all switch mode designs, and the reason being that it often switches extremely quickly, sometimes in the order of 100 picoseconds. So we need to treat it just like we treat any other high-speed digital signal, which means that we definitely need an unbroken reference plane below the signal, and ideally it's implemented in a strip line configuration, which means it's sandwiched between two unbroken planes. And if we look at the Rev B 4-layer design, we can see that the track is buried on layer 3, and the reference plane layer is predominantly the bottom layer, which is layer 4. And that's because the stack up they've used, the track is more tightly coupled to layer 4, because the spacing between layer 3 and layer 4 is much tighter. It's 12 mils. Compared to 32 mils between layer 2 and layer 3. So even though there's a break in the copper on layer 2, I'd expect the effect on the gate drive signal to be not as bad as if there was a gap on layer 4. So this change likely helped to contain any noise emitted from this specific track. And one other thing they could have done here to limit the EMI caused by this track is to add a series resistor next to the controller. And this has the effect of reducing the slew rate of the signal, which limits the amount of noise, especially at higher frequencies. So if you observe ringing on this track, then try adding a series resistor somewhere between an ohm and 10 ohms perhaps. It does come with a cost though, which is increased heat dissipation in the PFET, because it takes a bit more time to transition from on to off, and that translates into reduced efficiency. And if you're designing switch mode power supplies for automotive requirements, then the conducted emissions test requirements can extend up into the hundreds of megahertz. And this gate drive track in particular can be responsible for emissions above 100 megahertz. So really make sure you treat it like a high-speed digital signal trace. And as with any other high-speed digital signal, you also need to make sure that the IC is adequately decoupled so that the current required by the high-speed driver can be sourced locally from the decoupling cap. If you have inadequate local decoupling, the power supply and ground rails are likely to have increased voltage noise, and they can potentially radiate effectively as well. Now moving on, another major difference between these two designs is what's called the critical current loop. And you can check out why current loops are so important for EMI control in episode 1 on this channel. But for this case study, what we'll be focused on in particular is the capacitor C2 and C6 and how they interact with the switching FET Q1. And as we'll see, these form what we call the critical current loop, which is ultra important for us to optimize to control EMI. So let's look at what we mean by the critical current loop. To discover what the critical current loop's all about, let's zoom out and revisit the buck topology. And the best way to visualize this, I think, is to imagine where the high frequency current is flowing in a buck topology in the two separate switch states. So when the switch is on, the current flows through S1 and L1, then returns via the bypass capacitor C out. That's one of the reasons it's important to include a high frequency decoupling cap on the output of your switch mode, as well as a larger bulk capacitor, because bulk caps aren't very good at bypassing high frequency current. Also, if you're using an electrolytic cap here and you're failing conducted emissions on the main switching harmonics, then you can try using a tantalum or a hybrid cap here instead, which generally offers a lower impedance. But moving on, when the switch is off, current stops flowing through S1, but we have energy stored in the magnetic field of the inductor, which flows around this path here. So the next thing to do is to visualize how the current in both of these loops changes over time as the FET switches on and off. Is it a fast rate of change or is it slower? Let's take a look for both of these loops. Well, the first thing we can see is that the current through ID1 and IS1 have very abrupt changes of state. The rate of change of current is very high at the rising and falling edges here and here through Q1 and through D1. But then we have the current through L1, and the rate of change of current in the inductor is restricted by the rate that the magnetic field can expand and collapse. So the rate of change of current in this loop is a lot more gradual, and it isn't as big of a concern for us. So therefore we can identify the critical current loop as this one here. It's the loop with the highest rate of change of current. And if we can minimize the length and area of this loop, we reduce its inductance and we reduce the ability of the loop to radiate and generate conducted emissions as well. And that's our goal. So how do we minimize the effect of this critical current loop? Well, probably the simplest and most effective way is to place your components very carefully so that the root lengths and the loop area are minimized. And that includes things like making sure that the components all remain on the same side of the PCB if possible, so you don't need to use vias. And also the orientation of the components makes a big difference to the overall loop area. And the other thing we can do is to use a bypass capacitor to shorten the route for the very high frequency current in the critical current loop. If we place it across the FET source to ground, like I've shown here, then you can see that we can significantly reduce the length and area of the critical current loop. And you can also compound the effect of this decoupling cap by adding 2 or even 3 in parallel, which further reduces the inductance of the loop. That can be especially useful for automotive designs or other designs like wireless, where you want to make the conducted emissions as low as possible up into the hundreds of megahertz. Now, looking at the TI Rev A design, the critical current loop is formed by C6, Q1, and D1. And on the layout, the loop is here, and by my measurement, it's about 38 millimeters in length. That's 11 millimeters on the top side and the bottom side, and 8 millimeters on either side. So 38 millimeters in length. And flipping over to the Rev B design, the current loop has been reduced to about 18 millimeters. So it's it's under half of the length. It's 5 millimeters on the top and bottom and 4 millimeters at the side. So the loop length has been more than halved, and the area has been reduced by more than a factor of 4. And on other projects I've worked on, specifically high current DC-DC power supplies up into the hundreds of amps, I've seen optimization of the critical current loop give improvements of 5 to 20 dBs across a wide band of frequencies, from the low megahertz region up into the hundreds of megahertz. But before we move on from the critical current loop, I want to also mention that the addition of an extra 2 layers has also allowed the designer to provide an unbroken copper pore on the 3 layers behind the loop. Now, this advanced technique can really improve the EMI, because the magnetic field created by the loop can induce eddy currents in these copper pores, which produces an almost equal and opposite magnetic field. And so you get flux cancellation, which has the effect of reducing the overall magnetic field produced by the critical current loop. And that's really what we're after. The one exception to that in this case is the ground via here, which would ideally move down here so that the copper pores below the critical current loop are completely unbroken. But for the most part, this is much, much better than Rev A, and I would expect on the Rev B unit that there's a much lower EMI on the bottom side of the PCB, and especially if you're using a heatsink to wick away the heat on the bottom side of the PCB. This is going to limit the amount of noise propagation to that heatsink, because you've got the magnetic field shielding in between. Okay, so I've got a little demo here so that you can see this critical current loop in action. And what you can notice is, as I move the probe around the board, these emissions kind of, they peak, they go up, and they go down. So it depends on how much energy is inductively coupling to this probe. But as I move over the critical current loop, you can see that it goes up, and that's because the largest rate of change of current is in this area here. And in fact, the peak is over the inductor, is directly over the inductor, and that's because the inductive coupling is highest right there. There's a number of turns on the inductor, of course, and so the inductive coupling is higher to the inductive probe. And that's why you'll see a lot of inductors with magnetic field shielding above the coil. And in fact, that's why it's better as well to use a toroidal coil for a switch mode if you're going high current in particular. So you'll see a peak there and a peak above the critical current loop, but elsewhere it begins to drop off fairly quickly. So let's jump back across to the computer now, and we'll take it from there. Now, the final difference I'm going to highlight between the Rev A and the Rev B units is the addition of the snubber network across the diode. And essentially what these guys do is to help to limit the rate of change of voltage. And it just consists of a resistor and a capacitor, and they're connected in series from the switch node to ground. It's used to damp the parasitic inductances and capacitances during the switching transitions. And what it does is it reduces the ringing voltage and the frequency, and also reduces the number of ringing cycles. And because we reduce the voltage and the current ringing, we also minimize the amount of common mode noise that couple through parasitic capacitance to any heat sinks. So typically it reduces the measured common mode current by the LISN, or the line impedance stabilization network, used in the test setup. And these plots from TI, and it's app note SLYT465 if you're interested, it shows the effect that snubbing networks can have on a switch node voltage in a buck design. This one has both high side and low side FETs, but you get to see the effect of the snubbers anyway, and as you can see, it's quite a huge difference. So I would expect quite a large difference in terms of EMI performance. Okay, so let's do some measurements now to quantify the difference between Rev A and Rev B. So what I have here is a line impedance stabilization network from TechBox, and these are available from the EMC FastPass online store if you need to get a hold of these. And also, this is a transient current limiter. This one isn't from TechBox, but they actually do one as well, and again that's available in the EMC FastPass store. The link is below this video. And then it's connected to my spectrum analyzer here. What we're looking at, we're going to do this in 3 separate bands. So we're looking at the 150 kilohertz up to 5 megahertz right now, and we're looking at the Rev A board. So what I'm going to do is just capture this trace, and then we'll compare between the 2 boards as well. So as we compare these two, this is really interesting. So the blue is Rev B, the yellow is Rev A. And what's interesting is that the lower frequency switching harmonics are predominantly the same up to about here, which if I put the marker on is up to around a megahertz. And I think the reason for this is that these, the main switching harmonics are taken care of by the bulk capacitors. So this critical current loop doesn't have much of an effect down in the lower frequencies because the capacitor involved can't supply the charge for the main switching current. And it even peaks there, it's a little bit higher between, say, 1 megahertz and 2.5 megahertz. So there appears to be like a resonance that's introduced somewhere around here. But as we go higher, the Rev B begins to come into its own here. So we're down about probably 10 dB. So 2 megahertz upwards, we're down approximately 10 dB. And then as we get closer to 5 megahertz, then we're down about maybe 5 dB or so, which is still a lot. But let's go up higher now. Let's look at the higher frequency range to see what happens. Okay, so here's the Rev B performance. Blue, again, all the way up to 30 megahertz. Low end is 150 kilohertz. So that noise level is pretty low. And we'll compare to Rev A in a second. And just a reminder, this is a pre-compliant setup. I'm not using ground planes to standardize the parasitics. The cable layout isn't great, but for comparative measurements between Rev A and Rev B, this should be fine. So I'm going to do peak hold and then store this, and then we'll compare it to Rev A. Okay, back to Rev A now on the yellow. So let's do max hold, see what we have. So again, that's interesting. What we have is Rev A performs worse in the band approximately 1.6 megahertz up to 10 megahertz. And then it's approximately the same up to about 15 meg, and then it's flat. So about actually 10 dB worse from from 15 meg all the way up to 30 meg. And for commercial limits for, say, the FCC or CE mark for Europe under CISPR 22, typically the upper frequency limit is 30 megahertz. But for automotive standards and some other conducted emissions standards, you need to go higher than this, not necessarily using a DC listen. Sometimes the conducted limits are specified as a current clamp measurement. But for automotive in particular, we're interested in the conducted emissions performance as it goes above 30 meg, because if noise is coupled to a cable harness in a car, then that can radiate pretty well. The cable harness can radiate pretty well, and it can interfere with the many wireless transmitters that are on board in a car, such as Bluetooth, Wi-Fi, cell phone. Typically all of that is built in now, and the antenna structures are actually put onto the windows in the car. So let's extend this now up to, say, 250 megahertz. And again, we're looking at Rev A here. And these two blips here, they're ambient. So this is radio transmitters that are being picked up by the cabling in the test setup here. So don't worry about these two blips, but I believe this overall frequency profile is actual conducted emissions. Now, this DC listen isn't characterized all the way up here. So there's probably resonances that that this introduces into the measurement circuit. So it's not going to be super accurate for full compliance measurements. But again, in terms of comparative measurements, as we compare Rev A to Rev B, it's going to be super useful. So again, the yellow one is Rev A between 150 kilohertz and 250 megahertz. So that includes the FM band, the DAB radio band, and some other bands as well that are important for automotive standards. So let's save this and then move over to Rev B for the final sweep in this case study. Okay, back to Rev B, switching this on here, trace 2, max hold. Look how interesting that is. So you can see how much lower the noise is there, up into the hundreds of megahertz. So not only is this really important for passing conducted emissions limits, but probably more importantly for electronic design as we implement more and more wireless transmitters into our designs, this is a much lower noise power supply. So there's less chance of interference with onboard wireless transmitters in our designs, and this is really the way you want to go. So we're seeing improvements there of 10, 20, 30 dB. So yeah, this is a vast improvement. And I heard from TI engineers as well that this Rev B device is compliant with European standards for CISPR 22 as well. So big improvement there all around. So that really highlights the importance of the critical current loop, the layout, and the snubber circuit for conducted emissions performance. So I think that's pretty conclusive. Okay, so that's it for this video. Hopefully that was informative for you. It certainly surprised me the way the way this performed, especially in the higher frequency range. So hopefully you can use these takeaways for your next switch mode power supply design, and not only will you have a better chance of passing conducted emissions, you're probably also going to have better performing wireless devices on your board, because your switch mode is going to be far less noisy and it's going to conduct far less noise on the power rails. So that's it for now, but make sure to like and subscribe and add me on LinkedIn. The link is below the video, and there's some more resources below the video as well, so check that out. But that's it for now, and check back for more EMC content in the future. Cheers.